Hi, my name is Leo Rivera, and today we are going to talk about soil moisture release curves. And our focus today is going to be understanding the technology behind making those measurements. And when it comes to understanding the technology, I really think it's important to understand the history behind the measurements and how things have evolved over time. So the earliest tools for measuring soil moisture release curves arose in around the 1920s. And that started with things like the filter paper technique and the pressure plate method. Those are some of the traditional methods that have been around and have been used for a long time for making these measurements. In the 1950s, tools came along to measure based on what's called the vapor method. And those tools measure a sample in equilibrium and measure the vapor pressure of that sample to try and actually determine what the water potential of that sample was. And then in the 1960s, we came out with the evaporation method. And that method has evolved a little bit as well over time. All of these methods have evolved to some extent over time as the technology has moved along and come along. But these have been some of the early tools for making these measurements, and all of them have had their challenges, but many of them are still used today. And today we're going to focus on a couple of methods. But before we dive into the methods, another key point to understand about making the measurement is some of the challenges. And one of the main challenges behind making water potential measurements is the limitation of the ranges of all of these devices. And so here you see a graph on the right that shows the range of water potential measurements that these devices are capable of making. And so here you can see, for example, the pressure plate versus the HYPROP versus the WP4C, which is a dew point device, and the VSA, which is vapor sorption analyzer. On the right, we have our field methods. We're not going to focus too much on that today. But you can see the challenges with these devices is that none of them really cover the full range of water potential. And ultimately, that's our goal, is to understand the full soil moisture release curve. And so typically what we have to do is combine the tools together to make those measurements. And one other key point to hit on here is you can also see that although some of the measurement tools cover a good part of the range, they have limitations due to accuracy and things like that. So these are some of the challenges when it comes to making the measurements and trying to measure the soil moisture release curve. So one of the primary methods that we use today to measure the soil moisture release curve is based on the evaporation method. And the tool that we use for that is the HYPROP. So the way the HYPROP works is it starts with a saturated soil core. And within that core, we have two tensiometers that are measuring water potential or moisture potential at two different points within the core. And that sample then sits on a scale, and it's measuring the change in water content as the sample is evaporating. And at the same time, we're measuring the change in water potential with the tensiometers at the two different points. And so those two measurements together allow us to measure the soil moisture release curve with this device. One challenge with the HYPROP is it is somewhat limited in its range. Tensiometers are more so wet end tools for making the measurement on the soil moisture release curve, as I showed in the graph before. And so because of that, we need to combine this device with another method to make those measurements. The device that we like to combine that with is based on the chilled mirror dew point technique. And again, one of the common tools used for making that measurement is the WP4C. You can see an example of what that looks like here. And the way the WP4C works is you start with a sample that is sealed in the chamber with that device. And that chamber reaches vapor equilibrium with the sample along with reaching temperature equilibrium. And what we're doing is we're measuring the sample temperature and the mirror temperature continuously as that is coming to equilibrium. And then at the same time, we have an optical sensor that is detecting the presence of dew formation on that mirror that is being chilled and warmed with a Peltier cooler, and it's cycling through that until that dew formation occurs, and we're trying to detect exactly when that dew formation occurs. Hence why it's called the dew point technique. And so what's really nice about this method that works based on what we call as the Kelvin equation to convert that relative humidity measurement to water potential is it has a really wide range that it can measure. It can measure from about 0.1 to 300 megapascals or about 100 kilopascals down to about 300,000 kilopascals. So really broad range that it can measure. And what's nice is now we can pair the two tools together to get the full soil moisture release curve. So here you can see an example of how we've paired the HYPROP with those data points on the left, along with the WP4C with the data points on the right to generate the full soil moisture release curve, so we can actually characterize that soil completely with the two instruments together. Another method that we'll touch on just a little bit that works similarly is a device that utilizes what's called the dynamic dew point isotherm. And this device is called the vapor sorption analyzer, or VSA. And this device operates on similar principles to the WP4C. It is a dew point device, But what's really neat about this device is at the same time as it's making those measurements, it is able to pass dry air over the sample to dry it and wet air over the sample to re-wet it. So we can do drying and wetting curves with this measurement automatically and generate soil moisture release curves that look like what we're seeing here on the left. And what's really neat about this is this gives us so much more detail about the drying of the soil moisture release curve that we've never seen before. And it's helping us answer a lot of questions about soil properties that we've never been able to answer before. So another approach that we can use to make soil moisture release curves is actually by combining field measurements to do this. So here we're going to show you an example of combining a water potential sensor like you see on the left. There we're using the Terrace 21 along with a water content sensor like the Terrace 12 in a profile, and we co-locate those sensors at the same depth to measure the water content and water potential over a season at the same time. So this is an example of what that looks like in one of our field measurements where we have two sets of sensors at 8 centimeters and 15 centimeters. And on the top, you can see the water content measurements over time. And then on the bottom, you can see the water potential measurements over that time. And we decided to focus in on one drying period to try and see if we can actually generate the soil moisture release curve based on that drying trend from those two sets of measurements. And this is actually what that looks like now. So now we can combine those water content measurements with the matrix potential measurements to generate the moisture release curve for those two different points in the soil, which does vary a little bit because the soil change a little bit due to organic matter and different things at those different depths. And so we can actually use these methods together to generate in situ soil moisture release curves. And so as we're thinking about these methods that we've talked about, one of the things that you need to remember is some of the factors that can impact accuracy. It's always important to understand the limitations of the devices that we're using to make measurements. And some of those things that you need to think about are equilibration issues. And so this is historically some of the issues that we've seen with tools like the filter paper approach or the pressure plates, is that we oftentimes can have equilibration issues that result in errors due to the measurements. And also with traditional methods, we've struggled with not getting enough measurement points to actually resolve what's happening in the soil moisture release curve. No method covers the entire range. So unfortunately, we're still at the point where we're going to have to combine two methods to try and get the full soil moisture release curve in most cases. And so it depends a little bit on your applications. In some cases, you may only need the wet end of the soil moisture release curve. And in other cases, you may only need the dry end of the soil moisture release curve. But these are things that you need to think about when it comes to choosing the devices that you're going to use to make those measurements. And one other piece to think about is spatial variability and the sample size that you're using to actually make those measurements. And we'll touch a little more on this in a future video, but this is something that can also impact the accuracy of your measurements because small samples mean you're not always fully representing the variability that you can see in the field. And so that means you need to make more measurements. Here we have a moisture release curve on the left that we would say would be typically generated with a pressure plate approach. And now this is soilless media, so it's a little bit different than most soils. But if we were to generate a moisture release curve with just those points, you would say, okay, it looks fairly smooth. It doesn't tell us a whole lot about what's happening with that sample, but we can get a general soil moisture release curve with that. But with tools like the HYPROP, where we can get a higher resolution soil moisture release curve, we can then really start to dive into it and we can actually see, wow, okay, this sample has what's called a bimodal soil moisture release curve. That tells us a lot about what's happening with the pore size distribution in that soil and also can help us understand some of the things that might be limiting plant growth in that soil. And that was actually something that was super helpful for us when we were trying to dive into some challenges that we were seeing with this media. I've hit a lot today on the tools for making the measurements. And in our next video, we're going to focus on some of the best practices behind making measurements with those tools.